Okay, so let's do another example. Let's see. Example 3. Find the max and min of, excuse me, f of xy equals x squared plus y squared to the negative 1 power. Okay, so a slightly more complicated function here. In the region, we're going to add one more bit of complication here. In the region, x minus 2 squared plus y squared is less than or equal to 1. Okay, so now I've not only specified a function, I've specified a region, except now the region is given as an equation. So this is an equation of a circle that's centered at 2, 0. So let's go ahead and draw this out, because we can. Anytime you can actually draw a picture, it's always a good idea. So this is 1, this is 2, so this is the center of the circle. There's that, and there's 3. So we have a circle, and it's less than or equal to 1 of radius 1, okay? And it's closed. This is a closed and bounded region. So what we're saying here is on this region, all the interior points, including the boundary points, what is the maximum value that this function attains, and what is the minimum value that that function attains? Okay, that's all we're doing here. Well, let's just start and see where we go. So let's go ahead and take the df dx. So when we take the first partial derivative, this is going to equal negative x squared plus y squared to the minus 2 power times the derivative of what's inside, which is 2x. Okay, and df dy is equal to minus x squared plus y squared times 2y. So again, we're just taking the derivative of this function. This is a composite function, so we take negative 1 times this, minus 2 power, sorry about that, and then of course we take the derivative of what's inside. Since we're differentiating with respect to y, it's just 2y here. The first one we differentiated with respect to x. Okay, now notice, take a look at this. Well, for one thing, the function is not even defined at 0, 0. You can't have that because this is, okay, let me rewrite this. So this is going to be minus 2x over x squared plus y squared squared. And this is going to be minus 2y divided by x squared plus y squared squared. So first of all, this function is not even defined at 0, 0. However, for every other value of x and y, the derivative never equals 0. So df dx does not equal 0 anywhere on the domain, anywhere in the region. I mean, not that we were concerned with 0, 0, because 0, 0 is not even part of this, but anywhere on this region, the derivative does not equal 0, and neither does df dy. df dy does not equal 0 anywhere on the region in question. Okay, because the derivative does not equal 0 anywhere on that region, we know that it's not going to take place anywhere on the interior. So the max and min of this function is going to take place on the boundary. So it's the boundary that we need to concern ourselves with. And here's where it starts to get kind of interesting. All right, so let's go through this very, very carefully. Now, let me go ahead and move on to another page. And I'm actually going to redraw it so that I have it available for me. So I have this 1, 2, 3. Just do a quick drawing. So I have that unit circle centered at 2. All right, so the boundary is x minus 2 squared plus y squared is equal to 1. That's the boundary. The region was less than or equal to 1, but the boundary is at, okay. So how can we find the values of the function? Let me rewrite the function. So find values of f of xy, which is equal to x squared plus y squared. Let me write it actually as a fraction so that we have positive exponents. 1 over x squared plus y squared to the 1 power, so that's actually what we're looking. How can we find the values of this function on this circle? Okay, the value of this function on this circle. This is a composite function. I need to be able to take this, I need to be able to form f, so this is like I need to be able to form f of g. This is g, this is f. I need to form the composite function. Okay, here's what I'm going to do. I'm going to go ahead and parameterize this circle and express it as a function of one variable, t. All right? So let's go ahead and parameterize this circle. Well, I know what the parameterization of a circle is in general. Okay, so a general circle, the parameterization is just c of t is equal to cosine t sine t, right? That's the parameterization of a unit circle centered at the origin. But this one is not centered at the origin, it's centered at 2. So my parameterization for this function up here, x minus 2 squared plus y squared equals 1, looks like this, equals 2 plus cosine t sine t. If you were to put 0, pi over 2, 3 pi over 2, and 2 pi into t, you'll get this point, this point, this point, and this point. That is your parameterization moving in that direction. So this is a parameterization of this function. All I've done is taken an implicit function and I've expressed it parametrically. Okay, now I can actually form f of c of t. That's what's going on here. So c of t is this. This is f. I'm going to form f of c of t. So f of c of t is equal to, well, it's going to be 1 over x squared. Well, x is this. That's x. That's y. So it's going to be 2 plus the cosine of t squared plus sine of t squared. Okay, so now we're going to go ahead and actually multiply everything out. It's going to equal 1 over, well, 2 times 2 is 4. 2 cosine t is plus 4 cosine t plus cosine squared t plus sine squared t. That's the denominator. Well, cosine squared t plus sine squared t is the Pythagorean identity. That's equal to 1. So 4 plus 1. So my f of c of t equals 1 over 5 plus 4 cosine t. There we go. I found a way of expressing my function as a single variable, a function of t. This is my function. This is f of xy. Now, all I need to do is find the values of t that make this a maximum and to find the values of t that make this a minimum. All right. Well, this is actually really, really simple here. Notice this cosine of t. All right. So let's just, well, actually, let's just stop here. So let's just say f is a max. The function achieves its maximum value when the denominator is the smallest. When the denominator is smallest. And f achieves, this number here achieves a minimum value, the smallest value, when the denominator is the biggest. When denominator is biggest, right? This is the function. Big denominator, small value. Small denominator, big value. That's what's going on here. Okay, so now let's go ahead and find what this is. Well, what do we know about cosine of t? Well, the cosine of t has its biggest value of 1 and its smallest value at -1. It ranges between -1 and 1. Therefore, it's going to achieve, so cosine of t equals 1 when t equals 0. So we want this value here. We want to achieve the biggest and the smallest value. Well, we want it to achieve 1, and we want it to achieve -1. Okay. It's equal to 1 when we have cosine of t equals 0. Therefore, when t equals 0, that means the cosine of 0 is 1. That means 1 plus 5 times 4 times 1, it's going to be 1/9. Therefore, at t equals 0, that's when it's going to achieve its minimum value. Now, the minimum value of cosine t, cosine achieves -1 when it's equal to pi. So when t is equal to pi, the cosine is equal to -1. Well, -1 times 4 is -4. 5 minus 4 is 1. So now it achieves its maximum value there. So let's actually just write this out. Okay. Now, when t equals 0, c of t equals 2 plus cosine of 0 sine of 0 equals 3, 0. So that's the point at which it's going to achieve one of its extrema value. Well, f of c of t is going to equal 1 over 5 plus 4, which equals 1/9. That's the minimum. Now, when t is equal to pi, the cosine of t is equal to -1. C of t is equal to 2 plus the cosine of pi times the sine of pi, which is equal to 1, 0. Now when I put 1, 0 in to that function, f of c of t is equal to 1 over 1. Because remember, we had 1 over 5 plus 4 times cosine of t. 5 plus 4 times the cosine of t. When t equals 0, this denominator is 9. So it's 1 over 9. So that the value of the function at the point 3, 0 is equal to 1/9. When t equals pi, that's when it's at its smallest. The smallest value of cosine is when t equals pi. When t equals pi, well, cosine of pi is -1. 4 times -1 is -4. 5 minus 4 is 1. So the value of the function is 1. So at the point 1, 0, the value of the function is 1. That's the maximum. At the point 3, 0, the value of the function is 1/9. That's the minimum. So here's what we've done. This is our circle, 1, 2, 3. We have a circle here. That looks like an ellipse. Let's make it look a little bit like a circle here. Okay, we have this circle. So at the point 1, 0, here is where it achieves its maximum value of the function. At the point 3, 0, here is where the function actually achieves its minimum value. And we did this by just taking our function, parameterizing it, putting it into our region, okay, parameterizing the curve, putting that parameterization, forming f of c of t, like we've been doing for a while, and then we just found the values of t that make the function a maximum or a minimum. So the only real problem here is keeping track of all the mathematics. There's a lot on the page. There's a lot of numbers floating around. There's a lot of points floating around. The only thing you have to do is make sure that you differentiate between the point at which a maximum or minimum is achieved. In other words, these points, those are the points at which they're achieved, and the actual value of the function at those points. That's here, and that's here. So again, we want to rely on the techniques that we have at our disposal. But really what we want to rely on is our intuition and what we know about functions and how they behave and how numbers work. When you get to this point, you can reason out the rest. When this is the biggest, the number is going to be the smallest. When this is the smallest, this number is going to be the biggest. And you just need to go step by step and make sure that everything is there. Okay, I hope that this has worked out well. Thank you for joining us here at Educator.com and Multivariable Calculus. We'll see you next time. Bye-bye.